Hello, welcome to my number theory presentation on the continued fraction algorithm, also known as the CFRAC. So my name is John Paul. I'm a third-year student at the Australian National University in Canberra. So before I start this presentation, I would like to acknowledge the traditional owners of Canberra, the Ngunnawal people. I pay my respect to their elders, past, present, and emerging. So this video is actually my practice run. My official presentation is tomorrow. So I'm quite nervous so that's why I'm recording this early, just to get a feel of how tomorrow might go. So let's get into it. So I'm assuming that the viewer knows elementary number theory. So I won't be explaining like the extremely basic concepts. So the motivation here is, how do we find congruences x squared congruent to y squared modulo n, where x, y, and n are integers? So the continued fraction algorithm does this pretty nicely. So a little bit of intro and history. It was discovered by the mathematicians Lemur and Powers in 1931. And it has been described as a general purpose algorithm. That just means like it's suitable for factoring any integers n, and it's independent of the number's properties. So I'll introduce two methods, which I call the A method and the P method. The reasons why I call them that will be reviewed later on. And furthermore, the A method has been computerized by these two mathematicians, Morrison and Brilhart. And we will also see how efficient they have made it. So let's get into some continued fractions first. So we need to understand what a continued fraction is before understanding how the algorithm uses them. So definition: a finite continued fraction is an expression of the form like this, where the Qi's are integers for I greater than or equal to 0. So I have an example here. If someone were to tell you to write 8/5 as a continued fraction, you apply the Euclidean algorithm to 8 and 5 and basically work backwards and arrive at this. And alternatively, someone can give you this finite continued fraction and tell you to expand it. You can just proceed like this and end up with 8/5. And so this is a nice way to express rational numbers. And in fact, any rational number can be expressed as a finite continued fraction. Unfortunately, the representation is not unique, because any continued fraction that ends in a 2 can basically be split into 2 once. And that's pretty obvious from the definition. So now we introduce the concept of convergence. And convergent is basically just a finite continued fraction, except you chop off like a bit at the end. So for example, if you go back here, you might want to find the second convergent. Then you would just disregard this 2 and just look at 1, 1, 1. And you would just get a fraction out of that. And that fraction would be known as the convergent of 8/5. So from the definition, we have the theorem. So this is a nice way to compute convergence as well. So if you let Qn, so the Qn's are basically the Qn's in the finite continued fraction. If you define the following recurrence relation, so you define these two, and then for I greater than 1, define the integers ai and bi like this, then the kth convergent of this finite continued fraction is just ak over bk, and that's really nice. Notice that notice that this will never be less than 0. And I guess it's because how you define it like this. So in a continued fraction, only the first term, basically the one here before the semicolon, is allowed to be negative. So we can represent, so just now it was rational numbers. Now we can represent irrational numbers. And from the theorem here, this theorem basically says every x, if x is a rational number, if and only if it can be expressed as a finite continued fraction. Therefore, if x is irrational, you will expect that the continued fraction to be infinite. And we can use convergence to describe infinite continued fractions. Basically, an infinite continued fraction is the limit. It's the limit of a sequence of convergence. And I'll just bring up an example. So the example I have in mind is pi. So if x is pi, we know pi is 3.14159 blah, blah, blah. It's an irrational number. Its continued fraction expansion is, if I can find it, 3, 7, 15, 1. And it continues forever. So this is a bit of a random pattern. If you want to compute its convergence, you use the theorem before, but I'll leave you to check that out yourself. So A naught on B naught. So A naught is Q naught, which is 3. And B naught is 1. So 3 over 1, 3. A1, B1 is the famous 22 over 7. A2 over B2, 6. And if you were to compute the decimals of these fractions, you will see that they oscillate around pi. That means, so this is, so 3 is less than, but 22 over 7 is a little bit greater than that. And then this convergent is a little bit less than that. And so as you keep going, you get closer and closer to the actual decimal representation of pi. So yeah, like I mentioned before, pi has just this random continued fraction expansion, which admittedly is kind of annoying. But there is a class of irrational numbers whose continued fraction expansions are periodic. So they're infinite, but at least you know that there's a pattern going on in the in the continued fraction expansion. So I'll just introduce this definition. So a real number is a quadratic surd if it is irrational, and there exists a quadratic polynomial. So this is a polynomial ring. This basically says that your polynomial has integer coefficients. So a real number is a quadratic surd if it is irrational, and there exists a quadratic polynomial with integer coefficients such that a is a 0 of that polynomial. And then we move on to this theorem. So if a is a real number, then its continued fraction is infinite and periodic if and only if it is a quadratic surd. So perhaps some examples. What do I have? Root 2. So root 2 is the sorry, is it has continued fraction expansion 1, 2, 2, 2, and like that. You can simplify this to like how you would notate continued decimal expansions. And you know that root 2 is root of x squared minus 2, and this is in the polynomial ring. And root 7, root 7, what is it? Memory serves me right. There are 3 1s and then the 4. So basically goes 2, 1, 1, 1, 4, 1, 1, 1, 4, and forever. And it's the root of x squared minus 7. So how about something that's a little bit more special, the golden ratio? This is the simplest continued fraction. So it's just 1, 1, 1, 1, 1. And this is the root of x squared minus x minus 1. Okay, so there's a difference between these two and with the golden ratio. And it's best illustrated by this theorem underneath. So let n, a natural number, be square free. That just means it's not a perfect square. So n can't be 4 or 9 or 16 and so on. So if it's square free, then the periodicity starts after the first term in the continued fraction of the square root of n. And I have here what it will look like for any square free n. So the periodicity starts after the first term, so after this q naught. And the periodicity goes like this. And this last term is twice the first term. So if you look at root 2, 2 is twice 1. And for root 7, 4 is twice 2. And just as another side on, this fact is irrelevant for what we will talk about, but I'll include it here. So the sequence Q1 up to QP minus 1 is symmetric, kind of like around the midpoint. So the summary from all that we've just said is, if we want to factor an integer n using the continued fraction algorithm, then we need to consider the square root of n and its continued fraction expansion. Okay, so we will now use 2 new integers. They are defined like this, so feel free to just pause and take a look at that. And then recall this theorem, how we define AI and BI. When used in conjunction with the PNs and the QNs, we get the following 2 equations. So we have minus 1 to the n, q to the qn equals this. And the second equation, like that. Yeah, now we want to reduce modulo n. So basically divide both sides by n. And what we get is, let's see. So for the first equation, it will be minus 1 to the n, Qn is congruent to like that. So because the second term is a multiple of n, it goes away. It's congruent to 0 mod n. And then the second equation gives us this after reducing modulo n. And I'll just define something very quickly. So this -1 to the n Qn will appear a lot. And honestly, it's a bit cumbersome to write all the time. So I'll just define this. So Qn tilde, I'll define it as that. And the viewer can replace it in any equation they see. So following on from how I define Qn tilde, we have Qi tilde is so equivalent. That's just the word that I came up with to Qj tilde if x squared Qi tilde is equal to y squared Qj tilde for x, y integers. You'll see why this is important later on. And now we move on to another theorem, and this will basically be the key driver in everything we do from now on. So let n be composite and x and y be integers. So suppose that x squared is congruent to y squared. So remember, the continued fraction algorithm will help us with that. But their square rooted form are not congruent mod n. Then the GCD, the greatest common denominator of x minus y in n and x plus y in n are proper factors of n. And here I've added like a nice little fact. So basically the probability that the GCD of x minus y and n is a proper factor of n is actually more than 50-50, which is quite nice. We want to find factors quickly. And so now we come back to the A method and the P method. So the reason why I called this method the A method is because it uses the A's, and the P method because it uses the P's. And later on, I will actually factor an integer using the A and the P method. And this is the integer that I'll use. And don't worry, I'll remind you what the number is. I'm just stating it here just for convenience. I should also say that all the theorems I've written down don't have proofs, just because I want this presentation to go quicker. I don't want to write down the proofs during the presentation. If you're looking for the proofs, then feel free to email me. So here's a table. So remember the QNs are the terms in the continued fraction expansion of your integer. So this is for n equals 1,329,000 or 13,290,059. Oops. So you got this long. I've calculated the first 41 terms, and here are the Pn, and this should be a Qn tilde, and here's the an minus 1 mod n, which have all came from these two equations here. Okay, so yeah, now we will get into the P method. So testing out the congruence for the P method. So basically, yeah, so behind the scenes, I have computed what this will look like for n equals, like 1, 2, 3. I haven't got them written down here, but I can quickly write it down. Let's see. If I just move this down a bit. So if n equals 1, we have minus q1 congruent to p1 squared mod n. I'll just do the first three cases. N equals 2, q2 p1 squared congruent to p2 squared mod n. N equals 3. There's a minus sign. P2 squared congruent to P3 P1 squared mod n. And you keep going. So this pattern leads to a proposition like the theorems not going to be proved. So let me bring this up again. Basically, you have this crazy looking congruence subjected to these restrictions as well, depending on the parity of K. Now, feel free to pause the video to absorb that in. So recalling what it takes, so recalling the definition of equivalence a few slides before. So we want to find instances where the indices, so this is the indice we're concerned about. We want to find when the indices I and j are of the same parity so that you can get this sort of congruence. And then what do we have? We have, so you can think of this as like x prime and this as y prime, and then this will look similar to this theorem here. And then you can use that theorem to factor your integer. And so notice that the x and the y's are also included inside the squares. That basically puts a constraint on what qn's you can use, because if you look at the table back here, you need to pick the qn's such that their values form a perfect square. You see what I mean by that later on. So here we go. So yeah, let's apply the previous slide to this integer here. So if you want to use just two qn's, so recall that for two qn's, you want to find when your indices are of the same parity so that you can get this instance. So if you look back to the table, so I've prepared this beforehand, so that's why I'll do this quickly. Notice that, I'll zoom in, notice that 25 and 29, they give the same factorization. So if you go back, so Q25 tildes, and they're equal to minus 5 times 571. And obviously 25 and 29 are both odd, so of the same parity. And so by our remark, we have minus Q25, P24, P22, P2 squared is congruent to P25, P23, P1 squared. I won't write mod n. And minus P28, P26, P24. So notice that P24 to P2 is also here with extra terms. P1 squared. And so what you can do is notice that P, what is it? Oh yeah, P25 to P1 is included here. So after P27, obviously it's P25. So you can literally just substitute this into the right-hand side. And because Q25 is equal to Q29, you can cancel them out on both sides. And if you do this correctly, you should get P28, P26 squared congruent to P29, P27 squared mod n. And lo and behold, you get back that. So this is like your X and your Y. And then you can factor using, so this implies that the GCD of P28, P26 minus P29, P27, and is a proper factor of n. Okay, so now you want to use more than 2 QNs. That's a little bit more tricky, but it's doable. We have to look at the QN column, so this column. So we want to use more than 2. So we have to pick the QNs such that their values multiply together to give a perfect square. So I have an example here. So you want to pick Q5. So Q5 has this, Q5, Q22, and Q23. So notice that if you multiply all those numbers together, you get 2 squared, you have 5 squared already, you have 41 squared, and you have 113 squared. So altogether, you get a perfect square. I mean, there are other values that you can pick here. You can pick 10, 26, and 40. And I'll let you check that that is right. So we will use Q5, Q22, and Q23. And this time we get so we have minus Q5, so P4, P2 squared, sorry. And then congruent to P5, P3, P1. Yes, that's right. We have Q22, P21, P19, P1 squared, P22, P20, P2 squared, minus like that. And you have 3 congruences this time, but the method to solve them is the same. You kind of just substitute one after the other. And in the end, you should get 5 squared. I should write them in brackets. So 5, P23, P4, P2 squared. So all of that gives you this congruence. And then this is another instance of the theorem. Great. And now for the A method, the A method is, in my opinion, and I guess objectively, a much more efficient and quicker method than the P method. So if we want to use 2 QNs, also I have here, so this is for 2 QNs and this is for multiple QNs, more than 2 QNs. So using just 2 QNs, we actually, oh yes, right. So we will go back to Q25 and Q29. So, but this time we use this congruence instead. And there are less things to calculate. So you have minus Q25 congruent to A24 squared mod n, and minus Q29 congruent to A28 squared mod n. And so, because we already know that Q25 and Q29 are the same, this means A24 squared is congruent to A28 squared mod n. And we have another instance of the theorem. To use more than two QNs, so using Q5, Q22, and Q23 again. So Q5 like that, Q22, I should put a negative sign, and congruent to A21 squared. Q23 is A22 squared. So recall that Q5 is 2 times 5 squared times 41. Q22 is Q22 41 times 113, and Q23 is equal to 2 times 113. So you want to now you want to use this formula. Yep. So you want to put A21 and A22 together. You'll see what I mean. If A21 and A22 are here, and A4 is here, so these will be squared. Notice that this gives you 113 and a 5. So notice that the 2 and the 41 cancels out on both sides. So feel free to pause the video and try this out yourself. And again, this is an instance of the theorem. So summary, the equivalence, so that definition of them being equivalent is key. I have here quite painful to calculate using the P method. And yeah, I mean, even if you get the congruence, like check it out, you have 21 P's to calculate the product, which is quite, yeah, it's quite painful. So if there are multiple QNs, I definitely suggest going on to the A method, because you can just multiply the ANs without having to check whether they form a perfect square. And then because of this efficiency, the A method was computerized by Morrison and Brilhart. So now let's move on to their algorithm, which computerizes the A method. So the definition, an integer n greater than 0 is called B smooth if there exists a B in the natural numbers such that the prime factors of n are less than or equal to B. So I can just give a quick example. So like 24 is is 3 smooth because 24 is 2 cubed times 3. And I guess because you already know that 3 is in there and 2 is less than 3, it's not too smooth. No pun intended. Okay, so this is quite a packed slide, but let's work through the steps one by one. So they want to perform Gaussian elimination in modulo 2 on row vectors. And these are the steps they took to get to the vectors. So 1, focus on the composite QNs. So back in the table, notice that some of the QNs are not factored. That just means that they're prime. So therefore, in this method, you don't consider them at all. You pick an upper bound B, and then you form a set called the factor base. And inside the factor base, it's just going to be prime numbers less than or equal to B. So you want to pick your B sufficiently large. Also, you should always include -1, just because of the fact that there are minus signs in front of some, like each QN with odd indices. Okay, now you use the QNs whose prime factors are in the factor base. So if you don't understand what this step means later on, there's going to be an example. I'll talk through it. I'll talk through all 7 of these steps clearly later. So for the B smooth QNs, so if a QN has prime factors which are in the factor base, it is by definition B smooth. So then for the B smooth QNs, you define the vector Vn whose entries correspond to the multiplicity of the prime factors of Qn modulo 2. So your row vectors can only have entries 0 or 1. Then you form the matrix whose rows are the Vn's. And then you just find linear dependencies among the row vector Vn's. So just some linear algebra work here. Let S be the set of I such that Vi is in linear dependency. So if V1, V2, V3 is linearly dependent, then S is just the set 1, 2, 3. It's just the index of the vectors. Then you define the product of the QN such using the indices in the set S. And this will always give you a square number. Lastly, you just let X equal to this product of the ANs, and then you're done. It just gives you this, which satisfies the theorem. Okay, example. Can put this into application. Same integer. I picked B equals 113, and this is my factor base. So all of these guys are primes. So according to how F is defined, we will use these Qs. So if I go back, so say 41. So 41's not in here. That means, unfortunately, we can't use, for example, Q5, because even though 2 and 5 were in our factor base, 41 isn't. And then obviously, like these numbers, they're too big, not even in our factor base, which means those QNs are not 113 smooth. And then I might write down, so Q10 is equal to, I have my notes here, I can read them off here, what their factorization is. So Q10 is 31 times 43. Q23 is -2 times 113. 26 times 31 times 53. Q31 -2, 5 squared, 113. Q40 is 2 times 43 times 53. Okay, so running through here. So 0 because -1 doesn't appear in the factorization of Q10. And then 31 and 43 appear once, like that. Very easy, and then the rest are zeros. Here, Q31 has 5 squared, so 5 appears twice, but 2 is 0 mod 2. That's why there's a 0 here. Hopefully that explains why all these entries are 1 and 0. So it's basically this step again. The multiplicity is mod 2. So then you form the matrix. I just making this table a little bit neater. It's just this matrix. Then since it's modulo 2, you actually don't really need to do Gaussian elimination. It's very easy to just look at the rows and just trial and error, try and sum them up, see if you get the 0 vector. And you get these two, you have 2 linear dependencies. Then, so because 10, 26, and 40 give us 1 linear dependency, this is your S. It's 10, 26, and 40. And then you just form this product. And notice that it's a square. It will always give you a square. And here, 23 and 31 give us a linear dependency. So this S is 23 and 31. It gives you a square. You do the same with defining X. So the 2 sets are equal. And here and here. So unfortunately, using the first dependency, this doesn't give us a proper factor of n. So we're looking for proper factors. Like this method does give us a factor. It's just that we don't want that one because it's either 1 or the original number back. But if you use the second dependency, so the one with 23 and 31, you do have a proper factor of n. So then you just make the congruence like this. And then this is an instance of the theorem before, which implies that the GCD of this minus, I forgot. Should be like this. And that gives you a proper factor of n. Let me just look through the rest of my notes and see if there's anything I missed out on. I should probably say what n actually factors into. So 3, 1, 1, 9. And to find 3,119, you can just change the negative sign to a positive sign, and it gives you the other factor. But notice that, recall the theorem that I said, it's x minus y with n whose GCD is a proper factor of n, which has a probability greater than 50-50. So I just have one last thing. So what if 41 was in the factor base? Well, then you add 41 in to this column. And before I said that we couldn't choose 5 because 41 wasn't in the factor base. Now we can choose 5. And I believe there's another Qn with 41 as a factor. 22. So Q5 and Q22 are our 2 new Qn's in addition to these 5. So you can just add it in. I did this earlier, so I'll just have a quick peek at my notes. So you would get So here's 5, 10, 22, 23, 26, 31, 40, 1, 1, 0, 0, 1, 0, 0. Bear with me as I fill in all these values. Okay, so, and then the linear dependencies this time. So I think there are 3 linear dependencies this time. So you have, I'll just mark them in different colors. So you have 5, 22, and 23, which was, I think, yeah. So it's these 3 guys. And then the other dependence is 10, 26, and 40. So 31 doesn't have anyone to be with. So it is its own dependence. And to top it all off, here is, I guess, how you would program the continued fraction algorithm. So you can feel free to pause the video and have a look at that. I'm not much of a programmer myself, so I haven't done it on Python or anything. And yeah, that finishes the presentation. Final remarks. Thank you for listening. So I hope to use this presentation as motivation to make more maths videos. Yeah, I'm thinking of expanding onto YouTube. I want to reach more people using my math skills. So thank you for listening to my presentation, and I'll stop there. Thank you.